as the temperature increases, the length measured will not be accurate because the length of the ruler changes. Alright, let's look at another problem. A bridge 100 meter long is built of steel. By how much will its length change from the coldest winter of -30 degrees Celsius to the hottest summer of 40 degrees Celsius? Well, what we need to find here is delta L. We know delta T, we know the original length. Can we find delta L? What's an equation that we can use for delta L? Well, delta L equal to L1 alpha delta T. Is that right? Alright, we got L1 100 meter. Delta T is final temperature minus the initial temperature. 40 minus -30, that is 70 Kelvin. Alpha is known, therefore delta L is alpha L delta T. And using all the given values, that delta L is 0.077 meter. Look at this. When temperature increases, the length of the bridge increases. So, if you are training to be an engineer, a civil engineer for example, tell me, is it safe to build a bridge between two fixed columns? If you build a bridge, suppose this is a bridge built between two fixed columns. Is it safe to build it like this? When the temperature increases, the length is going to increase, and if it is built between two fixed columns, there is nowhere for the bridge to increase its length, so what's going to happen? It's going to buckle and break. So, in order that the bridge may remain safe, bridges are normally erected on rollers so that there is room for expansion and movement. The same thing can be found in the construction of railway tracks. The rail tracks, there are spaces left in between rail tracks to allow for expansion. If expansion is not taken care of, rails expanding against each other will buckle and then derail the train, can cause great accidents. If you look at your driveway, when concrete slabs are placed to build your driveway, now do we make one full concrete slab for the whole driveway? No, we don't. We break them into slabs and allow a space between them. Why? Because when temperature increases and decreases, cold winter to warm summers, there are tremendous changes in temperature, especially in Florida. That means the concrete slabs will be expanding and contracting. We got to allow space for this to happen. And if you don't allow space for this to happen, the concrete will crack. Now, if you look at some driveways, you can see those cracks where those spaces were not properly provided. So all these have great application in building industry, in civil engineering. Okay, let's do another example. The density of aluminum is 2.7 times 10 to the 3 kilogram per meter cube at 0 degrees Celsius. What is the density of aluminum at 200 degrees Celsius? Again, what all you need to solve this problem is the relation between density at T degrees Celsius and density at 0 degrees Celsius. What is that equation? dt equal to d0 times 1 minus gamma delta t. So we need density at 0 degrees Celsius, that is given to us. We need delta T, that is given to us, is that right? From 0 to 200 degrees Celsius. We need gamma, the coefficient of volume expansion, but we are given alpha. If you know alpha, do we know gamma? Yes, because gamma equal to 3 alpha. Alright, D0 we know, delta T we know, and gamma is 3 times alpha, and that also we know. We go to our equation straight away. D sub T equal to D0 times 1 minus gamma delta T. Now replace all these values, and there you have 2.66 times 10 to the 3 kilogram per meter cube is the density at that temperature. You can see the density has decreased considerably when the temperature is increased. Alright, another one. A hole is drilled in an aluminum plate with a steel drill bit which has a diameter of 6.24 centimeter at 20 degrees Celsius. In the process of drilling, the temperature of the drill bit and the aluminum rises to 168 degrees Celsius. What is the diameter of the hole in the aluminum plate when it has cooled down to room temperature? Well, in order to do this problem, we need to break it down into two pieces. The first one is the drill bit. Suppose this is the drill bit. As you keep drilling it, its temperature increases. The temperature of the drill bit increases from 20 degrees to 168 degrees. So the diameter of the drill bit increases. Now remember, diameter is a length. So you can use the equation L2 equal to L1 times 1 plus alpha delta T to find the diameter of the drill bit at that high temperature. Now, once you know the diameter of the drill bit at the high temperature, the instant when you finish drilling the hole, the diameter of the hole is also the same value. And now, what is the second part? The hole will now cool down, and you need to find the diameter of the hole when it cools down to the room temperature of 20 degrees Celsius. Alright, let's start the problem. You know, now don't confuse here, this D is not density. D20, what I mean is diameter of the drill bit at 20 degrees Celsius. That is what this D20 means. Diameter of the drill bit at 20 degrees Celsius is 0.0624 meter, 6.24 centimeter. The change in temperature of the drill bit is 168 minus 20, that is 148 degrees Celsius. Alpha for steel, can you remember that value? Well, alpha for steel is 11 times 10 to the negative 6 per Kelvin. The diameter of the hole at 168 degrees Celsius is the diameter of the drill bit at that temperature. So we can use the equation LT equal to L20, where L168 equal to L20 times 1 plus alpha delta T. And in place of L, we can use D, diameter. So D2 equal to D1 times 1 plus alpha delta T, where alpha is for steel. Well, we have all these values. Let's use those values there. D1 is 0.062 and alpha 11 times 10 to the negative 6, and the change in temperature is 148. That is 0.0625 meter. That is the diameter of the drill bit at the high temperature, which is the same as the diameter of the hole in the aluminum at that temperature. Alright, so diameter of the aluminum hole at 168 degrees is 0.0625 meter. Now it's going to cool down to room temperature. If dA1 is the diameter of the hole at 20 degrees Celsius and dA2 is the diameter of the hole at 168 degrees. A are used for aluminum. Diameter of the hole in aluminum at temperature T1, dA1, the diameter of the hole at 20 degrees Celsius. That is what we want to calculate. dA2 is the diameter of the hole in the aluminum sheet at T2 equal to 168 degrees Celsius. Then we have dA2 equal to dA1 times 1 plus alpha aluminum times delta T. Is that right? Yes. This is like L2 equal to L1 times 1 plus alpha delta T. Remember, in the previous equation, we were using steel because we were finding the diameter of the steel bit. So alpha value was for steel. This time, it is the hole in the aluminum, and therefore it is the expansion of the aluminum that we got to use, alpha for aluminum. We need to find dA1, so let's put down all the values. dA2 we know is 0.0625 meter. dA1 we need to find, and all these values. The alpha for aluminum is 24 times 10 to the negative 6 per Kelvin, and the change in temperature is 148 Kelvin. So simplifying the right hand side, we get 0.0625 equal to 1.00355 dA1, and therefore we can find dA1 as 0.0625 divided by 1.00355, and that is 0.0623 meter. That will be the diameter of the aluminum hole at that lower temperature. Now look at this. The diameter of the aluminum hole at a higher temperature at 168 degrees Celsius is 0.0625, and when the aluminum sheet cooled down to 20 degrees Celsius, the hole has shrunk. Its diameter is now 0.0623 meter. Alright, I want therefore you to think about this and give me a feedback. Just send me a line. An aluminum sheet with a hole at the center is heated to a higher temperature. Will the hole become bigger or smaller? Why? You have an aluminum sheet with a hole drilled at the center. As you increase the temperature of the aluminum sheet, will the hole become bigger or smaller? Why? Would you like to send me a line or two about it? Well, I might even give you a point if you do that well. It's a very important concept, alright? I want you to give it a thought. Okay, I'm going to stop this lesson here, and I will continue with this lesson, which is transfer of heat energy, in the next part. Okay, I will see you for that shortly.